Today, we're going to dive into the details of the WS2812B LED that's used on the circular display that we ordered from AliExpress in order to create our Fortnite chest. If all goes well, our final display will look something like the one in the video that you see here. Unfortunately, it takes a long time to get this particular display from China. It's somewhere in a warehouse or somewhere in a plane or who knows where. Hopefully it's on the way to my house. In the meantime, I ordered this strip of long WS2812B LEDs from Amazon. That strip arrived yesterday, and so we're going to plug it into our Microchip PIC and see if we can drive it. As you guys can see from the videos below, that has been successful. So let's take a look at the WS2812B and the protocol and details that it uses and how you can make it work with your own microcontroller. It's an RGB LED. It has 3 separate segments, 8-bit resolution per color, 24 bits overall. It's serially controlled, and it uses a proprietary digital time-based protocol that we'll talk about in a little bit. The datasheet says it requires 3.5 to 5.3 volt power supply. My samples worked. When I plugged them into 3.3 volts at reduced current, I never recommend running a part outside of its specs. Many LEDs can be cascaded together. This is how almost all the LEDs you see are used this way, in a string or 8x8 matrix, or in our case, a circular display. There's also a WS2812 version out there. This is an older version. It requires higher voltage. People say that it has worse color balance. Adafruit calls a variety of LEDs that use this control scheme NeoPixels. So occasionally you'll see that name as well. As far as the wiring, each LED has 4 pins. VDD, which we connect to +5, VSS, which we connect to ground, DN and DOut. The DN of the first LED goes to our microcontroller. That's how we're going to generate a serial command. After 24 bits are clocked in, it sends each additional bit out the DOut so it can go to the next LED. This takes a little bit of understanding to figure out how it works. The serial protocol is time-based. So to send a 0-bit, we send 400 microseconds high, followed by 850 microseconds low. On the system I'm using now, my logic input is 3.3 volts, even though my system is 5. That's working well. To send a high bit, we send 800 microseconds high, followed by 450 microseconds low. All values are plus or minus 150 microseconds. This is important because it's very difficult to hit these numbers right on the nose. When we take a look at that, with the tolerances involved, the initial 0-bit, the 0-bit initial value can have 250 to 550 microseconds high, followed by 700 to 1,000 microseconds low. So there's actually a fair amount of slack in there. For a 1-bit, it's 650 to 950 high, followed by 300 to 600 low. All of these are in the datasheet from World Semi, who makes the WS2812B. When we cascade multiple devices, data comes into the DN of the first LED, then goes out, the DO, into the DN of the second LED, then goes out into the DN of the third LED, and so on. Take a look at this diagram from the datasheet. This is a little bit different than other serially cascaded devices. For instance, you may have used the 74HC595 in the past to expand the amount of outputs that you have, say, on an Arduino or other things serially. These devices can also be cascaded, but in other devices I've used, the last device, the last data sent out, ends up in the chip that's closest to the microcontroller. This is opposite of that. The way that this works, as near as I can say, is that all of the LEDs look for a reset signal. As soon as they get the reset signal, that LED will capture the first 24 bits it receives. The D output will remain low until it's gotten 24 bits. After it gets its 24 bits, any additional bits that come in go out on the DO. If DI goes low for more than 50 microseconds, then you go into this reset case, and it'll capture the next 24 bits into the registers. But the registers will retain their prior value, and the LED will retain its color until the bits are replaced. So going back to look at this, we send in 24 bits. They go into D1. For the first 24 bits, D2 remains quiet. After 24 bits have been loaded into the first LED, then every signal that comes in D1 is propagated into D2. Then it fills up these 24 bits. So until we've sent enough bits to fill in both of the two LEDs, this line will remain silent. After both of these LEDs are full, these all act like pass-throughs, and the third LED gets its 24 bits. One of the things we need to note here is a potential risk. Once an LED is turned on, it'll stay on until it's commanded to go off. If your microcontroller locks up, the lights will stay in their last commanded state. This could be a problem if your circuit can't provide enough current to keep the LEDs lit, or if you count on it being able to turn off periodically to manage your thermals. So for instance, perhaps you have a whole bunch of LEDs that you're using like a strobe light. You blink them on for a fraction of a second, then turn them off for a relatively long period of time, allowing your circuit to cool. If for some reason your microcontroller locks up during the period that you're on, the lights will stay on until they're commanded off, which will never happen because the microcontroller is locked up. At this point, the system will be running at full power and 100% duty cycle, which potentially could exceed the capability of your circuit if it's not designed for that. The signal frequency required to drive the WS2812B is relatively fast compared to microcontroller instructions. The DI signal is approximately 1.25 microseconds per bit, or 800 kilohertz, and it has timing sensitivity on the transitions. Our PIC that we're using, the 24FJ256GA702, can theoretically execute an instruction every 63 nanoseconds. That makes it seem like there's plenty of time to generate these particular signals. However, we know that we have to be able to transition in less than 500 nanoseconds. That's actually only about 8 instructions, and that ability to execute an instruction every 63 nanoseconds is really only true when you keep the pipeline full, and it's assembly instructions, not C loops. So we're probably not going to be able to bit bang this, particularly if we want to be able to do anything else. We know that a requirement for this project is that we're also going to be generating sound, and that we're using an interrupt to generate that sound. It's likely that if that interrupt hit while we were trying to also drive the LEDs, we would mess up our LED timing. The solution to this is that we're going to use the SPI module to generate the pulses that we need. The SPI has 3 pins that are typically used: serial data in, serial data out, and serial data clock. The only pin we will be using is the serial data out. We'll let the clock go to an external pin just so that we can take a look at it. We're going to be able to clock this guy. The PIC24FJ256GA702 that we're going to be using has an internal FRC oscillator that runs at 32 megahertz. The M clock signal can be driven directly by that 32 megahertz clock. So we have 2 options. We can use the 16 megahertz clock that comes from the peripheral, or the 32 megahertz clock that we can get from the frequency reference output, which we'll have to configure separately. The SPI takes whatever clock it gets, divides it by the baud rate generator, and then requires 4 internal clocks for each clock of the SPI clock. So the fastest we could possibly run our SPI clock is 8 megahertz. Let's take a look to see if we can get by on the 16 megahertz peripheral clock, which is divided down to a 4 megahertz SPI clock. This would be a simpler configuration because we wouldn't have to use the frequency reference output as well. At 4 megahertz, each bit is 0.25 microseconds. So our T0 that we're shooting at to be 0.4, we could do 0.5 by doing 2 bits. That's 100 nanoseconds worth of error. The FRC is only accurate to plus or minus 1.5% at the temperature range that we're looking at. So we also need to take 1.5% of this nominal value and add that to our total error. For T0 low, we're shooting for 0.85. We can do 0.75 with 3 bits. For T1 high, we're shooting for 0.8. We can do 0.75 with 3 bits. T1 low, we're shooting for 0.45. We can do 0.5. So these guys don't look terrible. We're supposed to be able to get plus or minus 150 nanoseconds. It looks like our worst case with a 4 megahertz clock would be 112. It's not super, but it probably ought to work. At 8 megahertz, we can reduce the total error. Our target is 0.4. We can get to 0.375 by using 3 bits that are 125 nanoseconds long. If we're shooting for 0.85, we can get 0.857 by using 7 bits. If we're shooting for 0.8, we can get 0.75 with 6 bits. And if we're shooting for 0.45, we can get 0.5 with 4 bits. So you can see our worst case error on this is 60 nanoseconds compared to the desirable, whereas when we were using the 4 megahertz SPI clock, we were at 112. Using an 8 megahertz clock significantly reduces the worst case error. This feels like the right thing to do to me. So we're going to set up our Microchip PIC to use the 32 megahertz clock fed through the reference output that's then fed to the M clock input on the SPI bus. If we notice, at 8 megahertz, we have 3 bits followed by 7 bits to do a 0, 6 bits followed by 4 bits to do a 1. That makes 10 bits total. Fortunately, the PIC is sufficiently flexible that it'll let us pick the word length that we want to dump out. We're not limited to only 8 or 16 bits. We can also do 10-bit data. So it looks like the PIC should be able to very easily manage the signal that we want to output. Let's take a look at our hardware setup. We're going to be using the PIC24FJ256GA702. It's going to require a reset line that's pulled up. It's got a couple of different VDDs. They're not shown in separate places here that each require a bypass capacitor. And there's a 10 microfarad capacitor that's used for the internal voltage regulator. I've got a dev board that I use that generates 3.3 volts and ground and also does serial emulation if you want to use that for your particular board. For our WS2812 strip that I got from Amazon, we're going to feed it 5 volts. That's actually being fed off the USB over here. We're going to attach pin 26 RB15 to the DN. This is the data output of our SPI system. We'll set up RB14 pin 25 to show us the clock on the SPI. We don't actually need that, but since we're in development mode, it'll let us put an oscilloscope on it and see exactly what our clock rate is. Finally, we'll dump the reference clock out. We expect this to be 32 megahertz. Out this particular line, again, we can put a scope on it, and that'll help us verify that the system is clocked correctly. In our next video, we'll configure the PIC24FJ256GA702 using the Microchip code configurator that's part of the MPLAB X development environment. We'll create our application code, and once we get it up, one of the items that we were curious about is how much current the sky pulls. We'll measure a series of LEDs at different colors to get a current measurement. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting.